Okay, welcome everyone. So in this video, I want to review quickly the process that we've used in the past for diagonalizing a matrix when it's possible, and take a look in particular about what is special about this process when we are diagonalizing a symmetric matrix. So let's take a look at this matrix A, and notice this matrix A is symmetric. So the first column, 6, minus 2, minus 1. The second column is minus 2, 6, minus 1. And the third column is minus 1, minus 1, 5. And because entry A12 equals A21, entry A13 equals entry A31, and entry A23 equals entry 32, this is a symmetric matrix. And the diagonal entries, they can be anything that they want. So the way that we diagonalize a matrix is we first find the eigenvalues of that matrix. So in this case, you can verify that this matrix A has 3 distinct eigenvalues. Lambda is equal to 8, 6, and 3. And there's a link to a Colab document in the description of this video where you can go and check these calculations. But I would definitely encourage you to review how you find characteristic equations and how you find eigenvalues. Next, if possible, you find n linearly independent eigenvectors. And in our case, since we have 3 distinct eigenvalues, we know we've proven a theorem that the corresponding eigenvectors for each of these 3 eigenvalues, they are all going to be linearly independent from each other. So the fact that I see that matrix A has 3 distinct eigenvalues, that tells me matrix A can be diagonalized. But I want to be clear that we can diagonalize matrices if they have multiple, if they have eigenvalues with multiplicity bigger than 1, but we just need to be more careful in those situations. The eigenvectors are not guaranteed to be linearly independent. But in our case, we've got 3 eigenvalues, so we have 3 eigenspaces, and each of those eigenspaces can be generated by a vector, and those 3 vectors are going to be linearly independent. So again, I would definitely encourage you to review how you find eigenvectors and verify that for lambda equals 8, one eigenvector would be minus 1, 1, 0. For lambda equals 6, we have an eigenvector of minus 1, minus 1, 2. And for lambda equals 3, we have an eigenvector v3, which is 1, 1, 1. And once we find 3 linearly independent eigenvectors, then they tell us how we can construct a matrix P so that when we take a diagonal matrix of eigenvalues that we call matrix D, if I take P times the inverse of P, we get back matrix A. So the the matrix P that we choose has first column equals an eigenvector for the first eigenvalue of 8. The second column, we pick this eigenvector for the second eigenvalue of 6. And then the third column is this vector v3, 1, 1, 1, which corresponds for an eigenvector corresponding to the third eigenvalue of 3. And then the matrix D is going to be a diagonal matrix consisting of its eigenvalues in the appropriate order. So the first vector in column P was minus 1, 1, 0. That corresponds to 8. So that's my first diagonal entry. The second column vector of this matrix P was the vector v2, minus 1, minus 1, 2. This was an eigenvector for 6. So that is my second diagonal entry. And then the last column of matrix P was an eigenvector for our last eigenvalue of 3. And in this Colab document I've linked below, you can check that when I take P times D times the inverse of P, and this is an invertible matrix because all 3 of these vectors are linearly independent from each other, that we get back the matrix A that we started with up top. So let's take a look at what is particularly nice about the fact that this matrix A that we started with was symmetric. Okay, so let's continue working with this example. So we had three vectors, v1, v2, and v3, that were a basis for the eigenspaces corresponding to lambda 1 equals 8, lambda 2 equals 6, and lambda 3 was equal to 3, respectively. And then these three vectors we could use to form a matrix P that will help us diagonalize matrix A. But notice for each of these eigenvalues, we have many different choices of eigenvectors that we could have chosen. So any scalar multiple of these vectors I could use to construct some other matrix P that would also diagonalize this matrix. So this diagonalization process is not unique. So let's see what happens if I scale each of these vectors so that they're all unit vectors. So the first thing I want to point out is if I take the inner product, the usual dot product of v1 with v2, I can see I get 1 minus 1. So v1 and v2 are orthogonal to each other. If I take the inner product of v2 and v3, I get minus 1 plus 2 equals 0. So v2 and v3 are orthogonal to each other. v1 and v3, if I take the inner product of these two vectors, I get minus 1 plus 1. That is also 0. So it's worth pointing out and really emphasizing this, that we started with a matrix A that had three distinct eigenvalues, and therefore we had three eigenvectors, and these vectors were orthogonal to each other. And so this matrix P that we constructed from those column vectors, it has three orthogonal column vectors. But we've seen it's particularly nice to construct a matrix where the columns are orthonormal to each other. So we already have the orthogonality condition. Let's make each of these vectors unit length, right? So we're going to normalize each of these vectors by multiplying each of them by 1 over their length. So for the first vector, v1, right, it has a length of square root of 2. So the unit vector that has this identical direction would be minus 1 over the square root of 2, 1 over the square root of 2, 0. For u2, I would take and normalize this vector. This vector v2 has a length of square root of 6. So the unit vector in the same direction as v2 is minus 1 square root of 6, minus 1 over the square root of 6, and 2 over the square root of 6. And then for v3, it has magnitude square root of 3. So we scale it by 1 over square root of 3 to get the unit vector u3, which would be 1 over the square root of 3, 1 over the square root of 3, and 1 over the square root of 3. So by scaling these three vectors, we're not changing the fact that they're all eigenvectors for the same eigenvalues. We've just changed their length. And now when we diagonalize this matrix, we could choose to use this matrix P instead of the matrix P that we had on the previous slide. So again, this is not a unique matrix P that we choose. But we'll see that this matrix P is going to be particularly nice to work with because all of its columns are orthogonal to each other, and all of the columns have length 1. So when we take the product of P with P transpose, we're going to get the identity matrix. When I take the product of P transpose and P, we're going to get the identity matrix back. So it actually winds up being the case that P transpose is the inverse of matrix P. So when we diagonalize A, which is typically given by P times the diagonal matrix D times P inverse, we can just simply write that inverse as P transpose. So this saves us a calculation over here. Normally, we need to find the inverse of P, and that could take quite a bit of computational work. Much easier to just find the transpose of a matrix. So there's a lot going on here. Let's kind of unpack all of this a little bit more carefully. I've made some claims that I haven't quite proven just yet. Okay, so I want to summarize a really important observation that we just made in that previous example. And so first, let me define what it means to be an orthogonal matrix. So a matrix P is orthogonal First of all, it's a square matrix with orthonormal columns. So we've dealt with matrices where we have orthonormal columns where they're not a square matrix. So those would not be orthogonal matrices. But if we restrict ourselves to just looking at square matrices with orthonormal columns, then we get an orthogonal matrix by definition. And what's really special about orthogonal matrices is that we can find the inverse of an orthogonal matrix. It's just equal to the transpose of that matrix. So when we diagonalize matrices in general, we have P times the diagonal matrix of eigenvalues times P inverse. When we have this special case of a symmetric matrix A, then we can set up an orthonormal basis of column vectors. We found that each of the eigenvectors was orthogonal to each other. We normalized each of these vectors. So now this matrix P is orthogonal. And normally we would have to multiply on the right by the inverse of P. And this would be really difficult and computational heavy to calculate. But now we can just use the fact that P inverse is going to just equal the transpose of P. So in place of P inverse, I just take the transpose of this matrix and multiply on the right by the transpose, which is equal to the inverse. So there we've saved quite a bit of computations. So when we had this symmetric matrix, at least, we were able to construct a matrix P to diagonalize it such that this matrix P had columns which were all orthonormal to each other.